Hello students, Miss Slyman here to look at some separable differential equations with you. So we've seen how slope fields give us visual representations of different solutions. And over here, I came in and just tossed in some solutions that I was seeing and noting that at the top, it sort of looks like stacked parabolas, but then it reflects over the bottom. So I know plus C generally shifts things up and down, but it doesn't reflect things over. So let's go see what this original equation was. The original equation was that the derivative is the product of x and y. Well, that makes sense now why it's positive in quadrant 1 and the slopes were negative in quadrant 2, because quadrant 1, both x and y are positive, so their product is positive. In quadrant 2, though, x is negative, y is positive. That's going to give me negative values. Quadrant 3, they're both negative, so I get positive slopes. Quadrant 4, I'm getting my negative slopes. And of course, on my axis, I'm getting 0 slopes because one of those values will always be 0. So we might have thought if we had looked just at quadrants 1 and 2 that the original function was a x squared plus c, but we can see it's not. Furthermore, we know the equation that has, if our original graph is an x squared graph, we know its derivative is linear, like this. So my general solution, if the derivative is x, I know that that's going to be some sort of x squared graph because quadratics have linear slopes. But also notice that I could do this without just thinking about it. I could actually use algebra. So the first thing I want to do is isolate the x's with the d. I want to isolate x's and I want to isolate y's on either side of the equation. That's this word separable. I'm separating them out. So I'm going to take my dx, multiply it to the other side, and I'm allowed to do that. These are equivalent expressions. I could divide the dx back over here to get this, but it's nice this way because if I have them separated, well, integral dy equals integral x dx. Well, this is like integral 1 dy, which is just y. And I'm not going to write the plus c over here because if I add a constant here, I'm also going to add a constant on this side. And then I could just move this constant, combine it with this one. So it's better to just have one constant. All right, so let's go back to the original one where dy dx was xy. So now you want to isolate y's on the left, x's on the right. So I'm going to take dy equals x dx. X dx. This y I'll divide to the other side, so I'll call it 1 over y. And now I'll integrate both sides. Integral of 1 over y is ln of absolute value of y equals a half x squared plus c. Well, now I can do e of both sides. I get absolute value of y is e to the half x squared plus c. And then my y values, there was no restriction originally in domain and range. So that means that this value is plus or minus e to the half x squared plus c, which makes sense now why I had curves reflecting over the axes. So this is a separable differential equation. So when we're going to toolkit this, we want to think about isolating x and y on opposite sides of the expression. Let's go see here. So we're going to isolate our x and y, and then we're going to integrate, put a plus c on one side, and then get y by itself, thinking about whether you need to do a plus or minus. So here, plus or minus was allowed because there was no restriction originally on my y. All right, so when you're done toolkitting, go in and try the CYUs. You've got your answers here to look at. And if you have questions, post them in the question document, please.